Okay, picking up where we left off, the last thing we have to talk about, the last new rule after voltage drops are equal for different resistors and different branches in a parallel circuit. The current does not have to be the same in each place, but the branch currents have to add up to the total current, and the current into a junction must equal the current out of a junction, is the rule governing equivalent resistance. Now remember, equivalent resistance is like taking all the resistors in a circuit and saying, how big would a resistor have to be if we were to take all these resistors and replace them with just one resistor to get the same overall current out? And for a series circuit, this was very simple. You simply added up all the resistors. For a parallel circuit, it's not quite as easy. For a parallel circuit, the equation is as follows. 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 plus ... for as many resistors as you have. A couple of notes about this, okay? This is a very tricky equation to use because a lot of times people forget the very last step. A lot of times people solve for just this. This is the inverse of the equivalent resistance right here, 1 over Req. In order to get the equivalent resistance, you have to take whatever you got here and basically take the inverse of it. And I'll show you how to do that when we do the examples. The idea here, a couple of interesting notes, is that as you add more resistors, as you add more branches, you end up getting a smaller equivalent resistance, which, if the voltage holds the same, means you will have more current, which is very interesting. Okay, so why does this work? If you look at the equation here, the more resistors you add in, the bigger this side becomes, right? Even though they're fractions, as you add up fractions, you get a bigger and bigger number. But if you need to take the inverse of that at the very end, the bigger your number is right now, the smaller it will be once you have to take the inverse. And as a matter of fact, the other interesting point to note is that Req is always smaller than the smallest resistor. Okay? That doesn't mean adding resistors in parallel necessarily decreases your equivalent resistance. Every time you add a resistor in parallel, the equivalent resistance goes up, but the equivalent resistance will always remain lower than that of the smallest resistor. Essentially, how you can think of this is you're adding more paths for the circuit to go through, therefore there's less resistance, and since Ohm's law says V equals IR, less resistance with the same voltage, because that's just from the battery, that doesn't change. Less resistance, same voltage, must mean more current, more flowing charges flowing faster. Okay? So, before we get to calculation, I'm going to show you where all this information is located in the reference tables. Here's our reference table section on electricity. Everything we've talked about so far, we've talked about these 6 equations before. We looked at series circuit stuff. We know all the circuit symbols. We know the resistivity table. We had not yet touched on the parallel circuit section. And it shows us exactly what we just talked about. The voltage for the entire, the battery voltage is equal to the voltage drop for the first resistor, and the second resistor, and the third resistor. They're all equal as long as they're all in branches by themselves. Okay? It gets more complicated when we have what are called complex circuits, where there's more than one resistor per branch, or where you're mixing series and parallel circuits together. But we're not going to worry about that. The total current is equal to the sum of the currents in the individual branches. Total current equals current in branch 1 plus current in branch 2 plus current in branch 3, so on and so forth. And then here is the equivalent resistance formula that we just talked about. Okay? So let's apply this to some practice problems. Okay. So, our examples. What is the equivalent resistance of the partial circuits shown below? So let's just practice using that Req equation first. Our first has a chunk of a parallel circuit with a 25 ohm resistor in one branch and a 45 ohm resistor in another branch. Current flows in here, some goes this way, some goes this way. Meets back up here and flows out. So, to figure out the equivalent resistance, all we have to do, and yes, you do need the equation, 1 over Req equals 1 over R1 plus 1 over R2. That is equal to 1 over 25 ohms plus 1 over 45 ohms. Now, my suggestion here is to do the following. Take 1 over 25. You can write it down if you want. Maybe I will. 0.04. 1 divided by 45. Now that one's not quite as easy to write down, but we can. Okay, we're going to add those together. We get a certain number, all right? That is not yet your equivalent resistance. That is what 1 over the equivalent resistance is equal to. In order to get the equivalent resistance, there's a button on my calculator, and there might be a button on your calculator that means inverse. For mine, it's this, 1 over x. You might have a button that says x to the negative first. Either way, if I hit it, that will tell me the inverse of whatever I have. So that will essentially, if I get to the stage where I have 1 over REQ equals a certain number, some decimal, I hit that button, I now know what REQ is. If you don't want to do that, so say I had 0.06222222, there we go. That's what I originally had. The other way to get an inverse of something is to put it over, or to put 1 over that number. So if I do 1 divided by 0.06222222, I get the exact same thing. The equivalent resistance here is 16.07 ohms. Notice that it's smaller than either of these resistors, and not only is it smaller than the resistors, it also, what it's supposed to show us is if we were to replace this section of circuit with one resistor that essentially functions the same way, this is the size of that resistor. We can now go to this one where we have 3 resistors in series, or in parallel, and we'll figure out their equivalent resistance by 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3. That'll be 1 over 600 ohms plus 1 over 700 ohms plus 1 over 800 ohms. Now here's how I'm going to do this one. I'm not going to write down all the numbers. Instead, I'm going to be very careful, use the parentheses function on my calculator and do parentheses 1 divided by 600 end parentheses plus open parentheses 1 divided by 700 close parentheses. Notice that that value is 1 over 700, but because I had parentheses there, it remembers the number I had before. I got to add one more number, so when I hit plus, that just added those two together, and it gets me ready to add another, plus parentheses 1 divided by 800 end parentheses equals. That is what is equal to 1 over REQ. Now I simply press the 1 over X button, and I get that the equivalent resistance is equal to 230.14 ohms. Okay? So, you do have to practice that calculation a few times, but it is not too bad. Alright, now let's look at let's do some circuit analysis here. If we have a little parallel circuit here, we know the total voltage drop, or we know the battery voltage, which is the total voltage drop, 9 volts. We know the total current, 0.18 amps, and we know the resistance of one resistor in this parallel circuit below. Find the equivalent resistance, the resistance of the other resistor, the voltage drops for each resistor, and the currents for each resistor. So probably the easiest thing to do is to look at rule number 1. Rule number 1 says the voltage drops for each of these must be the same. So let me write that down. All voltage drops in parallel are equal. Okay, for the cases we'll look at, they're all going to be equal. So that means that this must be a 9-volt drop, and this. I just keep finding the places where my desk has a groove, apparently. Both of those are 9-volt drops. Now, we could do a couple different things here. I think what most people would do now is try and find the current through this resistor. So, I'm going to use V equals IR. The voltage drop for that resistor is 9 volts. We're looking for the current through that resistor. I'm going to call this resistor 1. And I'm going to call this one R2. Okay, so R1 is 150 ohms. if we do 9 volts divided by 150 ohms, we get that the current through this resistor is 0.06 amps. So what we can do now, we can do, again, a couple of different things. If we know the current here is 0.06, we can assume that the current through here, since I total must equal I1 plus I2, and I total is 0.18 amps, I1 we know is 0.06 amps, plus I2. I2 must be 0.12 amps. There you go. Okay? So there's the current through both resistors. Notice that they're different. Let's see, if I now know the current through this resistor, I should be able to predict its resistance. And let's see, that would be V2 equals I2 R2. We know the voltage drop for that resistor is 9 volts. We are predicting the current to be 0.12 amps, 0.12 amps, and we're looking for R2. Oops. R2 seems like it is about 75 ohms. Okay, so we've got the resistance of the other resistor, we've got the voltage drops, and we've got the currents for each resistor. We now have two different ways that we could find the equivalent resistance. We could use the equivalent resistance formula. 1 over Req equals 1 over R1 plus 1 over R2. As a matter of fact, I'm going to do that and show you that in certain cases, you probably don't even need to resort to the calculator too much if you're smart. 150, or clever, I should say. Okay, so our two resistances were 150 and 75. Notice that 75 is like a direct multiple of 150. Excuse me, the other way around. 150 is twice 75. And we know that if we're adding or subtracting fractions, we have to have a common denominator. So I could just do this. Say, let's see, 150 plus, if I multiply both top and bottom by 2, I get 2 over 150, which is, add those together, 3 over 150 is equal to 1 over Req. If I cross multiply those, 1 over Req equals 3 over 150. If I cross multiply, I get 150 equals 3 Req. Divide 150 by 3, you get an Req of 50 ohms. Okay? No calculator needed. Now granted, the numbers have to work out for that to happen, but you didn't need a calculator for it. And just in case you were wondering, I can, yes, do that on the calculator anyways. Okay? And we get 50. Perfect. Now, let's check this value. Okay? The other way we could have found the Req is if we take the total voltage, set that equal to the total current multiplied by Req. Total voltage is 9 volts. I is 0.18 amps, and we're looking for Req. And if I take 9 divided by 0.18, I get 50 ohms. It all checks out. Okay, so very basic circuit, parallel circuit analysis. Let's go and look at the real thing. Well, as real a thing as we're going to get. We can see that the battery voltage is 9 volts because I have my voltmeter placed around the battery. If I go and check out the voltage drop for this resistor, by the way, I couldn't do 150 ohm resistor on here. It didn't go up high enough. So what I've done is I've got two 75s right next to each other functioning as 150. I put the voltage, I place the leads around, I get 9 volts. I place the leads around this other one, I get a voltage drop of 9 volts. I see that my current is 0.18 amps. I'm going to go check the current in a few other places, so let's drag this over. This is 0.18. As soon as we get past that junction, it's now 0.12, and this should be 0.06. And if you notice, more current will go to the branch that has a less resistance. The resistance of this branch is 150 ohms. The resistance of this branch is simply 75 ohms. So what we have here is more resistance for a parallel circuit means that there's going to be less current there. The reason this works out mathematically is because you want to have the same voltage drop as every other branch. So if you have a branch that has a very, very big resistance, you don't have a lot of current flowing through it. If you have a branch that has not a lot of resistance, you get much more current flowing through it. Remember, atoms try and take the path of least resistance up to a point. The real rule is that the voltage drops have to be the same. More current will take the path of least resistance, if that makes sense. Not all current. We've got one more question to look at. We've already looked at one just like it, but we'll look at another one. What is the reading on the ammeter in the partial circuit shown below? We have a current of 5 amps flowing in, 3 amps flowing in, 7 amps flowing out, and an unknown flowing out. We know that current in must equal current out. If we have 5 amps plus 3 amps flowing in and 7 amps flowing out plus, I don't know, a question mark, 8 equals 7 plus question mark, well, the question mark must be 1 amp. And once again, we're going to demonstrate this on the computer. Here's our circuit. I've set this up beforehand. By the way, it would be kind of neat if one of you guys could figure out how exactly what the values of the resistors and the batteries would have to be in order to allow this to happen. I have 5 amps flowing in here. 3 amps here. 7 amps going out here. And we said 1 amp. Yes, that's exactly how it worked out. Okay, there's your basics on parallel circuits. I'll see you now that we're pretty much done with the 2 types of circuits we're going to look at. We're going to practice them a little bit, and then we'll move on to our last few topics in electricity.